Hello, guys, and welcome back to week 4. And this is going to be chapter 4. So we're going to focus on data transfer and how data is moved from the memory to the CPU and vice versa. Okay, and then we're going to talk about how data is accessed in the memory, and addressing means accessed. And then we talk about the arithmetic, basic arithmetic instructions like add, sub, and increment and decrement, and we're going to see their effects on the flags. Okay, and once we do that, then we're going to talk about the addressing modes. All right. So this is what we're going to be covering first. So we're going to talk about transferring data, okay, and the instruction that transfers data. So we're going to focus on these first, and then we're going to look at the basic arithmetics, okay? And once we do that, then we're going to talk about addressing modes, and then we're going to talk about creating loops, all right? Okay, so when we talk about data transfer instructions, we're going to talk about operands type, and we're going to talk about the instructions, and then we're going to talk about direct memory operands, and then we're going to talk about move instruction. And when we talk about move, we're going to think about how about moving data when the size is different, okay? And then how can we reduce the number of instructions, move instructions, by using an XCHG, okay? So let's look at the topic right here. So if you look at the operand types, remember this is the dot listing file that you played with in one of your labs, right? So this is the .sm file, the part right here, that is the .sm file. And this is nothing but the objective file, okay, which is we call the dot listing file, right, guys? So this part right here is the dot listing file, okay, or just call it dot object. Okay, so if you look at this part right here, you're talking about 8. So 8 is what? An immediate. So this immediate could be 8 of size 8-bit. It's a byte, 2 bytes, 16 bits, or 4 bytes, 32 bits. Okay, so the value, this 8, this value is encoded within the instruction. So when you write the code and when the instruction is actually translated, this is the operation code, part of the instruction is going to be a space made for the what? For the immediate, okay? And this space is going to be based on the destination. If the register is 32-bit, then this is of a size 32-bit, a range of 32-bit. And we already talked about this. This is going to be signed, okay? Not unsigned. Immediates are always signed, okay? Or it could be of a size 16, or it could be of a size 8. It depends on the register. If you are using 8 with EAX, or 8 with AX, or 8 with AL, or 8 with AH, either one, okay? So that way you are gonna have a different range for the immediate. So now we know that this is part of this instruction. So 8 is actually stored in the dot code because we know the instruction is stored in the dot code. So this is not something that we store in the dot data, okay? And then we have the registers. Here you have the register right here. Do you see it? The register EAX. So the register itself is encoded. So the register name is converted into a number because this is a human-like language, right? So if you look at the 8 right here, it's part of the instruction. If you look at EAX is encoded right here, right? So if I can look at it right here, it could be what? C0, part of the C0, because 4 is what? 4 is the immediate, so it's part of 83C0, so encoded within the instruction itself, the register name, okay? And if you look at the other operand type, it could be the memory, like the sum right here. Do you see it? So this sum right here, it is something that is going to be allocated in the memory, but we don't know for now because we're still translating, right? So that's why it has a space of what? 1, 2, 3, 4. So it's a space of 32-bit. Okay, because we declare it as a D word. Okay, so that is the equivalent of sum because that's the human-like. This is exactly what sum means to the operating system and the microprocessor. So these are the operands type, and these are their meanings. Okay, so keep that in mind, especially the immediate. And these are actually the operands notations. Okay, so this is what I mean by the notation. So you can move register to the register. So this is like a grammar, okay, or it is kind of a rule. So you have to pay very close attention to it. So you can move register to register. So when we say register, it could be of any size, right? If you look at it in here, it could be 1 byte, 2 byte, 4 byte, or we're just gonna say any general purpose register when we say this. So move works with any general purpose register. We can also move from register to memory. We know this is the destination, this is the source, right, guys? This is always the case. So we can move from register to memory, or from memory to register, or we can move immediate to memory, or we can move immediate to what register. So there is no immediate to immediate, or there is no memory to memory. So you need to know that move cannot handle memory to memory. Is that clear, guys? Can you look at the table, the other side of the table right now? I mean, the one in the left, and try to look at the what? Immediate right here. So you can have an immediate of size what? Immediate of size 8, okay? Or 16 or 32. If you just say immediate, it could be any of these, okay? And if we say memory right here, we can have memory 8, memory 16, or memory 32, or any of those. So this is what the notation is for, okay? And you already know in chapter 2 that these are the type of registers that we can have an access to if we are doing programming in the 32-bit program, right? If we are creating a 32-bit program. So these are going to be your your registers. These are going to be the size of your immediates, and these are going to be the memory, okay? So this is very important, and you might get back to that slide as many as you want, because as the time progresses, you're going to increase your knowledge, and that's going to maybe be the time when you're going to go and visit this the previous slide as many, as I said, as you need. And direct memory operands. So when we say direct memory operands, we're just moving a memory. So in this memory, we have var 1, and this is based on a memory of size 1 byte. And inside this memory, we have a value 10. Do you see it? So if we want to access this 10, we access it through the address. So we're going to say move var1 to AL. AL is a register. So we are moving from what? We are moving from memory to register, and that's what the move does, because we are talking about data transfer. Okay? So keep that in mind. You could also, in x86, you could also use the brackets. It doesn't really matter if you use the with or without brackets. It means the same. If you are using ARM assembly, which is a different assembly, you must use the brackets when you refer to a memory. Otherwise, it's going to be an error. But in x86, it doesn't matter. Okay? But in ARM assembly, it matters. All right? So if you see this or this, they mean the same thing. Here you are saying it very explicitly that this is memory. Here it's implicit, right? That this is memory. Just go and figure it out. Okay? And I would like you also to look at what we mean by dereferencing, okay? So sum is a human reference. This is the human reference. We need the CBU reference, okay? So that's what we mean by dereferencing. If you look at the sum right here, that is the reference for sum, okay? So sum is gonna be dereferenced. That means it's gonna move from just saying, for us, we say sum, and this sum maybe holds a value 10. So this something means, it has a meaning for us as a human, right? But the computer sees this as a 32-bit address. So it's gonna be dereferenced from here to there. So when we talk to the CPU, we keep it in this way. When the CPU talks to the human, we have to refer it back to what? To the sum. So that is what I mean by dereferencing in this slide. Okay, so that's very important. You need to understand that. So this is like the very important slide in terms of the move rules. So we know those rules. Okay, I mean, what moves can do, we understand that moves cannot do memory to memory. So we're going to look at the rules right here. Both operands must be of the same size when we use the move. Keep that in mind. So if you're going to say move to AL VX, that is wrong, because this is 16 and this is 8-bit, or this is 1 byte, this is 2 byte. This move cannot handle it. Okay? Both operands cannot be memories, and so we know that. We cannot say move to sum val1. We're going to look at that just in a second. That's not possible. Or we cannot use those registers as a destination. You might wonder why. Because the instruction pointer points at the dot code, right? So if you make this as a destination and you change its value, it's going to move from the dot code somewhere else, and that's going to corrupt your program. Okay? So the instruction pointer, 16-bit, the instruction pointer, 32-bit, the instruction pointer, 64 bits, cannot be used as a destination. Or those registers as well, the segments registers, if you remember, the ones that I said we are not going to cover. Okay? So let's look at this example. Why we have an error right here? Because this wval is a memory, that's fine. We can move memory to register. Nothing wrong with this. You see it, memory to register. But the problem is the size. This memory is of 2-byte word and AL is of what? 1 byte. So this is mismatch. This is, again, is an error, right? Count to EAX. So count is a byte. AX is what? Is a 2-byte, right? So we cannot mismatching. Though this is 2, the destination is larger, so it should handle that. Move cannot do it. If you do it, you're going to get an error. Play with that, please, in your Visual Studio. If you move count again to EAX, again, it's 1 byte to 4. This is 1 byte to 2. This is 2 byte to 1. So this cannot happen. Move cannot handle it. Okay, so let's look at this example and let's play with it a little bit together. So can we do this? Is this instruction correct? You guessed it right. It's incorrect. Why? Because this is the destination cannot be any of those registers. You see it? Data segment register, stacks register, and code register. It cannot. Okay? So this is the immediate move to those registers is not possible. And this is straightforward mismatch, right? We cannot move 2 to 4. How about this one? This is also not possible because we cannot have this register, the instruction pointer, as a destination. Okay? And again, what's wrong with this? We are moving 1 byte to an immediate. The immediate cannot be destination. But can you think why? Because the dot code, guys, remember, immediate is going to be encoded with the whole instruction. And the whole instruction is stored in the dot code. And the dot code is read-only memory. So you cannot write in the dot code. So that's why the immediate cannot be a destination. Okay? How about this instruction right here? So this should be fine. This is bval, which is a byte. And this is bval2, right? This is a byte, bval. Bval2 is a byte. So it should be fine, right? What is wrong with that? Can you think about it? I think you guessed it right. So we cannot do memory to memory because this says must be, cannot be memory. One of them has to be a register or an immediate. Okay, guys? All right. So another way to play around with moving, what if you want to move this to this? You know, you cannot do that, right? You cannot say move to var1, var2, because this is memory to memory. If you do it, you're going to get an error. But we can use a register, right? Because we know that's possible. So we move var1 to a register first, and then we move what we moved to the register, the value, to var2. You see what I'm talking about? So you have to have an immediate value, okay, or an intermediate value that's going to hold the value temper. It's like a temporary storage. So that's going to be a register. So you move it to a register, and that's okay, memory to register. And then you take from register to memory, that's okay too, as long as it's not memory to memory. Register to register is fine. Register to memory is fine. Immediate to memory or register is fine, but not a memory to memory. And there is something else that I would like to grab your attention to, which is the overlapping, okay? So if you have a storage space like this, an EAX, guys, okay? And let's say it has this value, 0, 0, 0, 0, 1, 1, 0. Okay, and let's say this is EAX. What if I say move to AL20? So if this is the previous value, this is going to be now overwritten, and now we're going to have 20, 0, 0, 0, 0, 1, 10, 1, 0, sorry, the 10. So this cannot be changed because we only access AL. This is AL, this is AH, this is AX. Right, guys? This is the AX. You with me, guys? So if you do this, this is going to change. All right, what if I say move to AH30? So this 20 is not going to change. We're only going to go here and move 30. because it's just going to affect AH. What if we say move to AX, let's say 1817. So we know that's 17 right here. It's going to take over this 20 now. So you're going to have 17, and then 18 is going to take 30. So this is now the new value. You see what I'm talking about? So keep that in mind. All right. So this is what we mean by overlapping. Look at this exercise right here, and you will see what I'm talking about. So every time you move part of a register to another register, just going to overwrite whatever the value you have in there. All right. And now we're going to deal with the data transfer instructions when we are actually dealing with the mismatching. Okay. So if we want to move, let's say, move to AX, AL. Oh, sorry, let me say it BL. So this is 1 byte, and this is 2 byte. If we do this, then Visual Studio is going to say an error. Okay, so what can we do about it? Okay, so you can play some tricks. These tricks used to be the case quite some time ago before Intel actually addressed this problem, the mismatching, and they come up with the specific instruction. But if you want to think about it, if you're going to copy smaller data to a large, so large to a small is not a question. That's not possible at all. But if you want to move small to a large, that's possible. But we need a different instruction. Okay, but let's look at the problem in general right here. So if you have a count, this is a word, and you want to move it to EAX, right? To ECX, I'm sorry. So that's mismatch. So what they did right here, they moved 0 to ECX. Why? Just imagine this is ECX, okay? And this is byte 1, byte 2, byte 3, byte 4. You know it, right? 0 to 31. So if you move 0 here, you are zeroing out everything. Right, guys? You with me? And then now you are moving what? You are moving count to what? CX, and that's fine because this is a word and CX is a value, right? So this is going to have what? It's going to be 0, 1, 0, 0, 0, 0, 0, 0. So in other words, you moved 2 words to a 4 words register, correct? So the idea of adding a 0 in here, you want to make sure that the left to this value is 0. So even if there is a leftover, it's going to be overlapped. And that way we're going to guarantee that the value is not going to change by having anything in the register because we zero it out already. That works if we are dealing with the unsigned. What if we are dealing with a sign, right? If we're dealing with a sign, it's going to be a problem, right? So this is what I was talking about here. Okay, so what if we are dealing with a negative number? So if we're dealing with a negative number, which is S word right here, and we want to do the same thing. So if we do this, keep this in mind, 0, 0, 0, 0, 0, 0, 0, 0, and this is 0 to 31. Keep this in mind that this 0 is a hexadecimal, right? So 0, 0, 0, 0 is going to be represented by 4, 0, 0, 0, 0. This is going to be represented by 4 as well. You see what I'm talking about? Okay, so the most significant bit, the bit 32, it's going to be 0. So that's going to say the value is what? Positive, regardless of what you're storing right here. If you want to store negative 16 right there, which is what? Negative 16 is going to be what? It's going to be FF. Okay, so negative 16 is going to be what? It's going to be FFF, right? So if you're going to say F0, so the most significant bit say 0. So this number is no longer negative 6. This number is 65,520. You see what I'm talking about? So this solution is not going to work, but I just want to show you that the extension is important. So we want to extend the sign in the right way. When it's unsigned, we don't care about the most significant bit because that means nothing in terms of the magnitude of the value. But when the number is assigned, it's going to be an issue. Okay, so to solve this problem systematically, we can use an instruction, right? That's just made for that. But before that, these are the games that assembly programmers use to play with. So what they did in here, instead of moving zeros to ECX, since you are dealing with the unsigned, they filled it with what? With negative 1, FF, FF, FF. This is negative 1 for 32-bit. This is negative 1 for a byte. If you don't believe it, just have 1, 1, 1, 1, 1, 1, 1, 1. So this is -1, right? If I want to show it to you, these are all zeros, right? 2's complement and add 1. So this is going to be 1, 0, 0, 0, 0, 0, 0. So this is actually 1. Since it's a negative sign, the most significant bit is a sign number, and it's 1. So this is -1. You see what I'm talking about? So you move this, and then you're going to move the sign value to CX. So if you moved it here, it's going to be FF, and then FF, FF. So it's not going to change anything. You see what I'm talking about? So this is something that you can do, but again, this is a very tedious way to do it. So x86, they came up with the specific instructions, and those instructions are MOVSX and MOVZX. So I'm going to explain those in a minute. So this is when we move unsigned, and this is when we move assigned bytes, okay? So ZX, that means always if you're moving something small, let's say this is EAX and you are moving BL, okay? I'm sorry. Okay, if you want to move this BL to here. So we're going to have BL here, no matter what the value is, right? Let's say if BL has a 5, okay? This is just for notation. Let's say if it has a 5. So we have 0, 5, and ZX automatically is going to extend the remaining with what? Zeros automatically. You see what I'm talking about? If we're going to say move to CXAL, again, that is your CX, and AL fits in here. Let's say if AL equal to 10. So we're going to have 10 in here, and automatically we're going to extend what? 0. So how many zeros we're going to extend? It depends on the destination. Right here, if the source is 1 byte, then we need to extend 3 bytes of 0. Here, if the source is 1 byte, but the destination is 2, so we need just to extend with 1. Do you see what I'm talking about, guys? So this is always going to extend with 0 after it fills the given bytes. Okay, let's say if I want to say move to AX to, let's say, EAX BX. So how many bytes this move ZX is going to extend? 2 bytes, because just imagine if BX equal to 7891. So if this is EAX, you with me, guys? So first we're going to have 91 and then 78, right? And the rest is going to be extended by what? It's going to be extended by zeros. You see what I'm talking about? So this is how the move works. The move ZX works. It's always extend with zeros, but it's going to say, what is my source's size? What is my source's size? And what is my destination size? And based on that, it's going to determine how many bytes of 0 it needs to add to the number. Okay, and this is what I was talking about right now. So if BL is this number, okay, so this is F, right? I think now you're very comfortable with the binary numbers, and this is 8, right? So if you do this, then it's going to add this to AX, okay, the first byte of AX, and the second byte of AX is going to be filled with what? 0, 0, because this is ZX, always extend with zeros. All right? And this is what I was talking about. So it's going to extend the other byte, which is AH, with the zeros, group of zeros, okay? All right, so this is like a very interesting exercise that you can play with. So you are given this number, okay? So keep in mind, this 0 is not part of the number, but why the 0 is added right here? If you declare or you define this number in Visual Studio and you take the 0 off, you're gonna get an error. Because when you start with a hexadecimal character, 96V, this could be a variable name. So the assembler is gonna be confused. Is this a hexadecimal number or it is a variable name? Because this could be a variable name, who knows, right? So to distinguish this, always if the hexadecimal numbers start from A to F, if the number and the most significant left, if it's A to F, then you have to proceed that with a 0. Okay, so that way you're telling the assembler, hey, this is not a variable name, this is a hexadecimal number, okay? So we have this number right here. This is 1 byte, this is 2 byte. This is just leading 0 to tell the assembler that this is not a variable name. So if you move ZX right here, you can see it, right? So we're gonna move first 9, B, and then A6, and then since the destination is 4 bytes and the source is 2, then the remaining is going to be 2 bytes. They're going to be extended it with what? With 0. If we say BL, this is the whole value of BX. This is the BL, right? This is BL, this is BH. So if you have 9B and then you have 3 bytes, 1, 2, 3, they're going to be filled automatically with the ZX zeros, okay? And this is again BL to CX. You're going to move this and then you're going to extend just 1 because the destination is a 2 byte. You filled it with a 1 byte, a small number, and the remaining is 1 byte. You filled it with 0. So look at the other example and you should be able to understand what's MOVZX. That is the easy way. Now when we go to the SX, that's the confusing part. So when we say SX, the only confusing part here is the most significant bit. If the most significant bit is 1, we extend with 1s. If the most significant bit of the source number is 0, then we extend with 0. So this is like ZX, okay? In the MOVZX, we always extend with zeros. In MOVSX, it depends. There's an F statement. What is the most significant bit? If it's 1, extend with 1, okay? Let me give you this number, 87 hexadecimal. Okay, so just imagine that this is AL, okay? Move to AL this part, and then we're gonna say move to SX what? Okay, let's say we're gonna say BX AL. So is this the most significant bit? Is it 1? This is a hexadecimal number. So we're going to say 8 means what? 0001. Huh, bingo. Always convert the number into binary so you know what is the most significant bit is. If it's a 1, then it's going to go to the BX. It's going to move 87, and here is going to say FF because this is 1. So it's going to be 1, 2, 3, 4. That's the first 4. 1, 2, 3, 4. So these are together. They're going to be what? 1 byte, right? 1 byte, which means negative. The sign is going to be extended. Okay, so keep that in mind. If the value, let's say, if you move to AL, let's say 71H. So 7 means what? 1, 1, 1, 0. So the most significant bit is a 0. So that means we are going to move the value and we extend with what? We're going to extend with zeros because the most significant bit is a 0. So we're going to say move this to BX, AL. We're going to have 71 in here and 00 right there. You see what I'm talking about? Okay, so always look at the most significant bit. If it's a 1, extend with 1. If it's a 0, extend with 0. I will write it here because most of my students, they think this is always the case. No, it depends on the most significant bit. In this case, whatever the value we're going to remove, we're going to put it here. The other one is going to be extended with what? With zeros. It depends on how many bytes. That depends on the destination. Okay, so if you look at this value again, should be an error. If you do this part in Visual Studio, you're going to get an error. So we have to have preceding 0 right here. Okay, remember that, please. So if this is my BX, so my BX is A69B, right? And we want to move this to EAX, right? This is my EAX. So we know, no brainer, right, guys? We're going to know that this is 9B and this is A6. So now I want to see, because this is MOVSX, am I going to say 00, 00, 00 here or FFFF? We have to look at the A. Since it's greater than 8, okay, then this is a negative number. Okay, right? So this is, we're going to say, let me just mix it. If it's A to F, then we know it's a negative number. Even if it's 8, it's going to be a negative number. So if it's greater than 8, greater than or equal to 8, then it's going to be a negative number, right? So keep this rule in mind. If it's less than or equal to 7, then it's positive. I'm talking about hexadecimal. Okay, hexadecimal numbers. So if that is the case, if I say A, I know even if you want to break A means what? 10. What is the most significant bit right here is 1. So you're going to extend with FF. Keep that in mind. And that's what we did right here. So this is the value, and we extended with 2 bytes because the remaining is 2 bytes because the number itself is 2 bytes. Okay, so keep that in mind. I would like you to play with the rest. All right, so this is if you compare ZX, always extend with 0, always. This one, F, just say F. If it's 1 or a 0, it's going to extend with 0 or it's going to extend with 1. All right, So that's the basic idea of the MOVSX and MOVZX. So that is when you are moving small to large, that is the way you handle it. When you move large to small, we have no way to solve it. Okay, guys? You with me? So far, so good. Okay, so now let's look at the exchange. So if we want to exchange memory to memory, that's not possible because whatever applies to move applies to what? Exchange. So you can move memory to register, register to memory, immediate to memory, right? But no immediate to immediate. The destination cannot be immediate. Whatever rules apply to move is going to apply to exchange, okay? The only extra rules that you have in here, no immediate. So you cannot exchange with an immediate. Can you think about it? Why? Why we cannot say exchange EAX with 5? Let's say EAX has a 10. So we're going to have 5 here. We're going to have 10 there. You see what I'm talking about? Okay. Why this is not possible? Can you think about it? Okay. Can you deeply think about it? So please pause the video and think about it. Okay. But anyway, we know that the immediate is encoded within the dot code, right? And dot code is read-only memory. So if you want to write 10 in this part, it's going to say, no, this is read-only memory. That's why it's prohibited. Okay, so that is the rule right here. You can exchange register with register, memory with register, or register with memory. Okay, so you should have this in mind. Why we need the exchange in the first place? Let's say if we don't have the exchange and I want to move, let's say I have AL has 5 and BL has 6, and I want to exchange it. I want to get 5 here and I want to get 6 right there. You see what I'm talking about? Okay. So if that is the case, then we're going to do the exchange, right? We don't have the exchange. We have to use the move, right? So we're going to say move to CL AL. And we're going to say move to AL BL. And then we're going to say move to BL CL. Do you see what I'm talking about? So first you kept the value of AL and CL. So CL has 5. Okay? Now you can change the value of AL. So the value of AL now is going to be what? It is going to be the other way around. I'm sorry. It's going to be, move this one is going to be 6. Or is it 5 here? Let me take this one out. So we moved this one to the 5. And then now we moved BL to AL. So BL has a 6. Then AL now has what? A 6. Okay? And CL has a 5. So we move CL, which is 5, to BL, so it's going to be what? A 5. So this is going to be a 6, and this is going to be a 5. So we needed what? 3 move instructions. Instead of this, you're just going to say exchange, okay, AL with BL. So it's going to give you the same effect. So after you run this instruction, you're going to find here you have 6, here you have 5 in one instruction, okay? But keep in mind, in reality, without an exchange, you have to do those 3 instructions, okay? All right, so this is when you're gonna exchange. This is dword, and this is 2 bytes and 2 bytes, so that's fine. Okay, you're gonna move VL to AX, and then you're gonna exchange. So you might wonder, why can't we just say exchange AX with val1? So maybe you don't wanna change the value of val1 because other part of your program, the other part of your program, they need still to use 1000. So if you don't want to do it, then you're going to move it to AX, and then you're going to exchange val2 with AX. So that way you're going to make this one 1000, this one 1000, but you don't want to change it. Do you see what I'm talking about? So you can do it in this way, or you can do it in one line, the way that you saw right here. Okay. So that is basically what the move instructions is all about. Okay. Is it clear how to handle the move? What are the rules? Memory to memory is not allowed, all right? Destination cannot be memory or the instruction pointer or the segment registers. How to deal with the different size, moving small to large, okay? Similar source like the memory, and we already handled the MOVZX and MOVSX, okay? And we looked at the exchange as well. All right, so we're gonna stop right here, and then we're gonna move on and look at the basic arithmetic. I'm just giving you a break so that way you're not gonna feel overwhelmed, okay? All right, thank you, see you later.